Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Students, today we shall undertake a detailed deep dive into the concept of the electric dipole. It is a crucial application within our unit on electric charges and fields. Our mission is to understand this concept simply and safely for your examinations. Let us begin with a small mystery. A very simple observation from everyday life that, well, it seems to defy basic physics. You have learned that uncharged objects do not attract or repel. No.
Yes, that's correct. Electrostatic forces act between charged objects.
Right. So if that is true, why does a simple plastic comb, after you run it through your dry hair, why does it attract tiny, seemingly uncharged pieces of paper? They just jump up and stick to it.
But if the paper is uncharged, there should be no force. No, the net charge is zero. What is the mechanism acting here?
And this is where the physics gets really interesting and very practical. The same principle is at work in everyday applications like LCD screens, the liquid crystal displays on your phone.
How so?
And even microwave ovens. In a microwave, tiny water molecules align and rotate in response to the electric field. It's this exact physics that heats your food. So to solve this mystery of the comb and to understand our technology, we must understand the electric dipole.
So it's all connected. The comb, the screen, the microwave, all working on this one principle.
Exactly. So let us start with the core idea. At the most basic zero level, what is an electric dipole? It is a simple but crucial configuration. Two equal and opposite charges, say a plus Q and a minus Q, separated by a small distance. That's it. Those are the only two ingredients.
Equal and opposite charges with some separation.
Yes. And to build a mental image, think of a magnetic compass needle.
Okay, I remember that from earlier classes.
A compass has a north pole and a south pole, two opposite poles, or you could say charges, separated by a distance. When you place it in a magnetic field, it doesn't move forward or backward. What does it do?
It rotates. It aligns itself with the field.
Precisely. It aligns. An electric dipole behaves identically in an electric field. Its main tendency is to twist, to align. Now, this concept is so important because, well, it's not just a textbook idea. It exists in nature. Real objects, like water molecules, are often dipoles. Their positive nucleus and negative electrons don't perfectly align, creating a natural, permanent separation of charge. Picture a barbell, two weights on either end of a rod.
Right.
The weights are the charges, plus Q and minus Q. The rod is the separation distance. Now, in a field, the forces push the positive charge one way and the negative charge the opposite way.
So they are being pushed in opposite directions, but they're connected.
Yes, and that is what causes the twisting, the rotation.
I have a question. If the charges are equal and opposite, should the total charge not be zero?
A very important question.
And if the net charge is zero, shouldn't the net effect just always be zero?
Yes, you are absolutely correct. The net charge of the dipole is zero. Plus Q plus minus Q equals zero. But, and this is the critical point, because the charges are separated by a distance, let's call it d, their effects do not perfectly cancel out everywhere in space. This separation gives rise to the critical property we call the electric dipole moment. Now let us see how Ensert defines this specific vector quantity, which captures both the charge and the separation.
Okay, you have it here. It says, an electric dipole is a pair of equal and opposite charges, Q and Q, separated by some distance 2a. Its dipole moment vector P has magnitude 2q and is in the direction of the dipole axis from xq to q.
Excellent. Let's break that down. The dipole moment P is a vector.
Meaning it has both magnitude and direction.
Yes. Its magnitude is simple. The charge magnitude Q multiplied by the separation, which the definition calls 2a.
Why 2a and not just d?
It is just a convention that simplifies many derivations later, because we often calculate fields from the midpoint of the dipole, so half the distance is a. But the direction, this is non-negotiable. For your exams, you must remember this. It is always from the negative charge to the positive charge.
Okay, from minus q to plus q.
Yes. And its unit is simply charge times distance, so coulomb meter. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's apply this. Let us consider a dipole placed in a uniform electric field, E, step by step. The force on the positive end is plus QE.
In the direction of the field.
And the force on the negative end is minus QE.
Opposite to the direction of the field.
Correct. So what is the net force on the dipole?
Since the field is uniform, the forces are equal and opposite. So they cancel, the net force is zero.
Precisely. The net force is zero. But these two forces are displaced. They're not acting on the same point. This creates that twisting effect we talked about. This is called torque.
Torque, right.
And the formula for this torque vector is the cross product. Tau equals P cross E. This torque tries to rotate the dipole to align its moment p with the field E. The magnitude of this torque is PE sin theta. And this relates to energy. The potential energy is given by U equals minus PE cos theta.
So when it's aligned, theta is 0, and the energy is at its minimum. It's stable.
Perfect. That is the key insight. Alignment is the minimum energy stable state. Let's do a very quick calculation. Imagine a dipole with a moment P of, say, 2 times 10 to the minus 8 kilometers. We place it in a field E of 500 newtons per coulomb at an angle of 30 degrees. The torque is PE sin 30.
Sin of 30 is 1/2, or 0.5.
Correct. So it becomes 2 by 10 euro times 500 times V, or 0.5. This calculates to 5 times 10 to the minus 6 newton meters.
That sounds incredibly small.
It is very small. But for a tiny molecule, that tiny torque is more than enough to cause it to rotate and align. And this understanding of torque and alignment, well, it forms the foundation for our next topics. Dipole alignment is the core mechanism behind polarization and how dielectric materials respond to fields. And that is essential for capacitors. Now, students, we must address 3 silent killers, 3 misconceptions that often cost marks in the board examination.
Okay, this is important.
Misconception 1, the net force. The wrong idea is that a dipole always experiences a net force in any electric field.
But we just said in a uniform field, the net force is 0.
Correct. The correct idea is that in a uniform field, net force is 0. The forces cancel. A net force appears only, and I mean only, in a non-uniform field.
Like the field from the charged comb.
Exactly like the comb. The field is stronger closer to it. This pulls the dipole towards the region of the stronger field. So you must remember this phrase. Uniform field rotates dipoles. Non-uniform field pulls them.
That makes it clear. Uniform means twist only. Non-uniform means twist and pull.
Perfect. Misconception 2. Alignment is instant. The wrong idea is that a dipole just snaps into alignment.
But there is a torque acting on it.
Yes, but torque causes angular acceleration. It's a gradual rotation. It's a process. It has to fight against thermal motion. So remember, torque causes rotation, which is gradual, not instant jumping. And the final trap, number 3, potential energy. The wrong idea is that the potential energy is highest when aligned with the field.
That does sound a bit counterintuitive. Why would students think that?
Perhaps because it seems like the most active or impactful state. But physics is about stability. The correct idea is that alignment is the lowest energy state, equals match PE. It is stable, like a ball at the bottom of a hill. The energy is highest when it's anti-aligned. That's unstable. Remember, alignment equals low energy equals stable.
So just to restate that first point, which seems the most critical, if the field is perfectly uniform, the dipole only twists. But if the field is stronger on one side, which is non-uniform, the whole dipole gets pulled toward that stronger side.
That is a perfect summary. You have understood it completely. Now, to make sure these facts are cemented for the exam, let's use some memory anchors. To remember the essentials, use the mnemonic DMT.
DMK.
D for dipole, which is 2 charges, M for moment, the formula P, LEQD, and T for torque, tau, P cross, EDMT. And a catchy phrase to remember what it does. Dipole moment from charged ends, field causes alignment torque.
Dipole moment from charged ends, field causes alignment torque. I like that.
And finally, a physical gesture. Hold your hands apart, as if they are the plus Q and minus Q charges. Imagine a force pushing one hand forward and the other hand backward. Feel that twisting in your body, that attempt to rotate until your hands are aligned with the field. That feeling is the torque.
Okay, I can feel that. It's a very clear physical analogy.
Good. Now, for your quick revision and exams, remember these 3 factual points about the electric dipole. Point 1. The dipole is a pair of equal and opposite charges, plus Q and minus Q, separated by some distance 2a. Point 2. The dipole moment, P, is a vector. Its magnitude is 2 kia, and its direction is, crucially, from the negative charge to the positive charge.
Okay, direction is key.
And point 3. In a uniform electric field, the net force on the dipole is 0. But it experiences a torque, tau, equals P cross E, that rotates it toward alignment. This is the foundation that links the tiny world of molecules to the large-scale technology you use every day. Students, to get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive into the electric dipole. We wish you success in your studies.